Okay, so you can start working on the problems. So I'll give a while for you to do the problems before going over them. We probably will end up finishing all of the questions. And so we're starting from number 5 because that's the first one that and also in the future, please try to have more people submitting. Although this week it's understandable because it's the AMC 10 and next week. Okay, so I'll start going over how this problem works. So there's a total of five pairs of socks, and so that's a total of 10 socks. And on Monday, Sandy takes 2 at random, and then on Tuesday, she takes another 2 from the remaining 8, and on Wednesday, she takes another 2 from the 6. And so you want to find the probability that Wednesday is the first day that Sandy selects matching socks. So you can think of these pairs of socks as slots or something like that with dividers in between and a total of 6 of them. And so you want to find the chance that these 2 don't match and these 2 match. And so first of all, we can let one of these 2 socks be at random, be some random color. And so let it be the 5th sock. And then so there's a 1 in 9 chance that the 6th sock, which it's paired with, is also of the same color. And that's because there's a total of 9 socks. So I can draw them here visually. And so the chance, and so let this 5th sock be like yellow, and then there's 9 socks left over, and only one of them is a match. So there's a 1/9 chance that these 2 match. And now let the 1st sock also be some random color. And this works because what happened in the first 2 days doesn't really affect this third. What happened in the first 2 pairs doesn't affect the third. And so you do not want these 2 to match. And since you already took out 2 of a color, and then now you have to take out another color because of this 1st sock. And now that leaves a total of 7 left over, and 6 of them are not the same. And so this is what? And so the probability of the 2nd sock not matching is 6/7. And now for this pair, so we can casework off of the color of the 3rd sock. So if the color of the 3rd sock matches with one of these 2, and this happens in 2/6 of the ways, because there's a total of 6 socks here, and 2 of them match with the previous. So that leaves a 2/6 chance of the colors being the same. And if this is true, then the 4th sock can be any random sock, because once you have 2 of the same color taken out, you can't get the same color again. So in here it's 2/6 times 1, and in the other case it's a new color, and this has probability of 4/6. And in this case, Alright. In this case, you would then have a different color taken out, and there's a total of 5 socks left over, one of which matches with the color of the one here. And so that's the probability of 4/5, that the colors also do not match. And so the answer is the chance that these two don't match, which is 6/7, times the probability that the third and the fourth don't match, which is 1/3 plus 2/3 times 4/5 times the probability. What? Okay. Please wait a while. Okay. Is it the same screen still? Okay. So the probability that these two don't match, which is 1/3 plus 2/3 times 4/5 times the probability that these two match, which is 1/9. And this is 2, 3, 5/15, 13/15. And so this is 26/315. And so you want to find the value of m plus n, which is 315 plus 26. And that's 341. So did anyone have any questions about that? Okay. So now we can go on to this problem number 6. And once again, I'll give a couple of minutes to do the problem first. And they're equally spaced on a minor arc of a circle. And so we can first draw the circle. Okay. Okay. And so this is points A, B, A, B, C, D, and E. And you're also given that there's a second circle, and it has center C, and points E, F, G, H, I, and A lie on the circle. So first of all, we can label these points A, B, C, D, and E. And now we draw a circle with center C. All right. So, and then you have that there's point E, F, G, H, and I, and A. E, F, G, H, and I. And then now you have that, and then the final thing you're given is that angle ABD equals angle AHG plus 12. All right. So first of all, we can let these arc lengths be, these 4 arc lengths be A, and these 5 arc lengths be B. All right. So for angle ABD, it's a inscribed angle for the circle for the first circle, and it has measure angle ABD has measure 360 minus 3a over 2, or 180 minus 1.5a. And now we can look at angle AHG. And similarly to angle ABD, it's an inscribed angle of the circle with center C. And so angle AHG is equal to 360 minus 3b divided by 2, or 180 minus 1.5b. And so you can plug these back into here, and what that tells you is that 180 minus 1.5a is equal to 180 minus 1.5b plus 12. And when you simplify this, it gives you that the relation a equals b minus 8. Now we can take a look at what we want to find. So angle BAG is equal to angle BAC plus angle CAG. And this is equal to, since angle CBA is another inscribed angle of the first circle, so angle BAC is 180 minus so angle BAC is 360 minus 2a over 2. Actually, hold. Sorry. Okay. Sorry. So angle BAC is an inscribed angle of the first circle, and it inscribes the arc of angle A. So it has measure A over 2. And if you look at CAG, well, you know that C is the center of the second circle. And so what that tells you is that you can extend this. And so the measure of angle CAG is also an inscribed angle, and it's equal to 180 minus 3b over 2. Yeah. And if you plug in a equals b minus 8 into here, you get that you're trying to find 172 minus 2b divided by 2, which is also equal to 86 minus b. And so now we just need to find the value of b. And to do this, we can see that angle ECA is equal to 5b, and it's also equal to 360 minus 4a divided by 2, which is 180 minus 2a. And so you have the equations a equals b minus 8, and 5b equals 180 minus 2a. And so you can plug this a into here, and so you get 5b minus 180 equals 2b, negative 2b plus 16. And when you calculate this, you get that b is just equal to 28. So the answer is 86 minus 28, which is 0.58 because AIMEs require leading zeros. So, does anyone have any questions about the solution? All right then. We can move on to the next problem then. And then once again, I'll give you a couple of minutes to do this problem before I start going over it. And so you're given points F and G on line CE and H and J on AB and BC. And it's such that FGHJ is a square. And now you have points K and L on line GH and M and N on AD and AB. And it's such that KLMN is a square. And so you're given that the area of KLMN is 99. So you want to find the area of FGHJ. Okay. So in this problem, the actual value of the area itself doesn't really matter much. It's the more better way to do it is the ratios of the areas. And so this side length to 2 and this side length to 1. And then you can calculate the ratio of these two sides and then square it and multiply it by the area of KLMN. Okay. So, and then another thing we can note is that this angle is equal to this angle, is equal to this angle, is equal to this one, is equal to this angle. So, and so all of those right triangles are the ratio of 1 to 2 to root 5. That's the ratio of their side length. And then so we can let the side length of these squares be A and B. And then so this is A. So this is 2 over the square root of 5 times A. And this is A divided by the square root of 5. And this is 1/2 A. So this side length, NH, is root 5 over 2A. And so now you have that this is equal to B. So this is equal to B over the square root of 5. And this is equal to 2B over root 5. And this is B. So this is 1/2 of B. And this is root 5B over 2. And now we know that ABCD is a square. And so that tells us that B over root 5 plus root 5B over 2 is equal to 2. Hold on a second. Alright, sorry. And so that gives 2B plus 5B divided by 2 square root of 5 is equal to 2. And so B equals 4 root 5 over 7. And now we can take a look at side length AB. And so similarly, it's also equal to CD, which is 2. So A over root 5 plus root 5A over 2 plus 2B over root 5 is equal to 2. And now, using the same thing here, we can quickly see that this is 7A over 2 root 5 plus 2 over root 5 times 4 root 5 over 7, because we've already found the value of b, and this equals 2. And then so this just simplifies to 8/7, so this goes to 6/7. And then so a is equal to 12 root 5 over 49. And so that tells us, and so we want to find the area of FGHJ. Hold on a second. All right. So for here, I'm going to use the notation square brackets to represent area. So FGHJ to MNKL is simply equal to b squared over a squared. And then we already found the values of b and a. So this is, we can take out the root 5 immediately. So this is 4/7 times 49 over 12 squared, which is 49 over 9. And so we're trying to find the area of FGH, sorry, FGHJ, and this is 99 times 49 over 9, which is 49 over, this is 49 times 11, which is 539. So does anyone have any questions about this problem? All right. If there are none, we can move on to the next question. All right. So I'm going to start going over this problem now. So for a positive integer n, let s of n be the sum of the digits of n. And so you want to find the smallest positive integer n such that the sum of the digits of n and the sum of the digits of n plus 864 is equal to 20. So first of all, if n is a 1 or 2 digit number, the sum of the digits can never be 20. And that's because the maximum possible sum of digits for a 1 or 2 digit number is at 99, and it's 18, which is still less than 20. And so let n equal 100a plus 10b plus c. And so clearly the sum of the digits of n is a plus b plus c, and you're given that this is equal to 20. And so now we can just first take a look at if it's possible for the 100th digit to not carry. And so if a is equal to 1, then you have that b plus c is 19, which cannot hold true for any 3-digit numbers. And now if a is equal to 2, you have that b plus c is equal to 18. And the only way this holds true for 3-digit numbers is 299. And 299 plus 864 is greater than 1000. And if the 100th digit is any larger, adding 864 will make it larger than 1000. And so that means that the 100th digit must carry. It always will. And so now we can split into cases on whether or not the other digits carry. Okay. So first of all, we look at the case where only the 100th carries. And if this is true, the thousandth digit is 1, and the 100th digit is a plus 8, and then you have to subtract 10 because of the carry, and it's b plus 6 plus c plus 4. And this is equal to a minus 1 plus b plus 6 plus c plus 4, and and this is equal to a plus b plus c plus 9. And you need this to be equal to a plus b plus c, so this case does not have any solutions. And now, let's take a look at the case where the hundreds and the tens carry. So in this case, the thousandth digit is once again 1, and the 100th digit is a plus 8 minus 10, but this time you need to add 1 because the 10th digit has carried and added 1 into the 100 digits. And we also know that we do not need to subtract 20 here because a plus 9 is always less than 20. So we don't need to carry a 2-digit to 1. We do not need to carry a 20. So, and now the 10th digit, because it carries, is b plus 6 minus 10, and the unit digit is still c plus 4. And this is equal to 1 plus a minus 1 plus b plus c minus 4 plus 4 is equal to a plus b plus c. And so this case works. And so now the restrictions on a and b, well, the restriction on a for it to be able to carry is just that a is greater than 1. And for b, it's b is greater than 3. And for c not to carry, c must be less than 6. And so in order to minimize the value of our number, we can focus on minimizing the value of a. And so to minimize a, we need to maximize b and c. And so the maximum value of c is 5, and the maximum value of b is 9. And so you want to find the value of a such that the sum of its digits is 20, and you can easily see that it's 695. All right. And now let's go on to the next case. And in this case, the 100th digit and the 1th digit carry. And so once again, this is 1 for the 1000th digit. The 100th digit is a plus 8 minus 10. The 10th digit is b plus 6 plus 1. And the unit digit is c plus 4 minus 10. And this is a minus 1 plus b plus 7 plus c minus 6, which is a plus b plus c. And now the restriction on the 10 digit not being able to carry is that the 10th digit must be less than 3. And the reason it's less than 3 is because the 10th digit is now b plus 7. And so the 10th digit is at most 2. And when the 10th digit is 2, you have that a plus c is equal to 18, and that already forces it to be 929. And if we try letting b be anything less than 2, then this fails. This just fails because then you have that a plus c is greater than 18, but this doesn't hold true for any combination of any digits. And now the final case is when all of the digits carry. And so in this case, the hundreds, the tens, and the ones carry. And so in this case, it would be 1 plus a plus 9 minus 10 plus b plus 6 plus 1 minus 10 plus c plus 4 minus 10. And so this is 1 plus a minus 1 plus b minus 3 plus c minus 6, which is clearly less than a plus b plus c. And so now we have the minimum values from the two cases that we showed have solutions. And clearly the smaller one is 6. So clearly the smaller one is 695. Okay, please wait. Okay, 695. So does anyone have any questions about this problem? Okay, I'm going to guess that there are none, so we can go on to this next question now. So you have an order triple A1, A2, and A3 such that they're all A1, A2, and A3 are all bounded between 1 and 10, and they're all integers. And so you're generating a sequence S with the condition that an is equal to an minus 1 times the absolute difference between an minus 2 and an minus 3. And so you want to find how many sequences there are such that you have an is equal to 0 for some value of n. So in order for an to equal 0, you either have that an minus 1 is also equal to 0, or an minus 2 is equal to an minus 3. So in order for it to be 0, it must fall under one of these two cases, an minus 2. And if it's here, we can split it into another two cases, where an minus 2 is equal to 0, or an minus 3 is equal to an minus 2. Oh, sorry, an minus 4. And this can just repeatedly go on until you have that a4 is equal to 0. And at this point, because you're given that all three of a1, a2, and a3 are greater than 0, so at this point you have to have that, and this will give you that a2 is equal to a1. All right. So that tells you that you must have two consecutive equal integers at some point. Okay. And so now you have that. If you have, so there's a total of 3 cases here. So the first case is when 2 of a1, a2, and a3 are equal. And this should be pretty obvious to me. This should be a pretty obvious case. And now another case is when the absolute difference between any of A1, A2, and A3 is equal to 1, between any two consecutive numbers of them. And there's a final case, and in this case, it eventually generates a pair of AI with difference 1. And the only way this happens is when the absolute difference of A1 and A2 is equal to 2 and A3 is equal to 1. And so those are the three cases. So first of all, we can deal with this case because it's pretty easy. So two consecutive numbers, sorry. And so in this case, you either have A1 is equal to A2 or A2 is equal to A3. You can have all three equal to each other, and we'll exclude this through PIE. So when A1 is equal to A2, there's a total of 10 times 10 ways to do this. And similarly for A2 is equal to A3. And the total number of ways to choose A1, A2, and A3 such that A1 is equal to A2 is equal to A3 is 10 times 10 times 2 minus 10, which is 190. All right. And so now we can move on to the second case, where the absolute difference between two consecutive terms is 1. So, for example, say you have that x minus y is equal to 1 first, and the total permutations are of x, y, and z. And so the number of ways to arrange this such that there's still a consecutive set of two numbers such that their absolute difference is 1. So there's a total of 4, and they're x, y, z, y, x, z, z, x, y, and z, y, and x. All right. And so if the values of those two terms are 1 and 2, then the number of possibilities for the third term will be 4 through 10, which is a total of 7 ways. And the same thing holds for 9 and 10. And there's the possibilities. All right. I'll pick up where I left off. So if the two numbers are 9 and 10, then the numbers will be from 1 to 7, and this is also 7 possibilities. And now, if the two numbers are 2 and 3, 3 and 4, all the way to 8 and 9, then in this case, there will be 4 numbers that you take out from 1 through 10, because you need to take out these two numbers and both of the numbers surrounding them. And so this is 10 minus 4, which is 6. And so when you exclude the number of ways to permute this, in this case, there's 7 times 6 plus 7 plus 7. And now you need to multiply in the fact that there's 4 permutations of each. And so this is equal to 224. And now you can look at the cases where the difference between each of the terms is 1. So if the difference is 1 and 1 for both times, then the starting term would be from 1 through 8, which is a total of 8 possibilities. And if the difference is -1 and -1 both times, then you would have that it's from 3 to 10. and this is also 8. And if the differences are -1 and 1, then the starting term could be anything from 2 through 10. And in this case, there's 9 possibilities. And if the differences are 1 and -1, then the starting number could range from 1 through 9, which also has 9 possibilities. Okay, all right. So I'll just start going over this problem. And obviously it will be today's last problem. So you have a triangle ABC with positive integer side lengths, and you're given that AB is equal to AC. So the diagram would look something like this. A, B, and C. Okay, that might not be isosceles, but it's fine. And so let I be the intersections of the angle bisectors. And so now let's suppose that BI is equal to 8. And clearly CI and BI are equal to each other because the whole diagram is symmetric across AI. And so you want to find the smallest possible perimeter of triangle ABC. All right. So first of all, we can add a perpendicular here, and it must go through I because it's an isosceles triangle, and AB is equal to AC. And so we can let AB have side length A, and this have side length B. And then we can use a bit of trig here. So this is theta, and this is theta. So cosine of theta equals B divided by 8, and cosine of 2 theta is equal to B divided by A. And also by using the cosine double angle formula, it's B squared over 32 minus 1. So this tells you that A is equal to 32B over B squared minus 32. And then so clearly B is positive. So in order for A to be positive, we need to have that B squared minus 32 is greater than 0, or B squared is greater than 32. And so this means that B is greater than 4 root 2, which is between 4 times 1.4 and 6. Okay. 6. All right. And this is 5.6. And so this basically tells us that B is at least 6. And now we already know that 2B is an integer, and B is also one of the legs of a right triangle with hypotenuse length 8. So the possible values of B are 6. Okay. 6, 6.5, 7, and 7.5. And so now we can plug each of these into this expression for A. And when we do, we see that all of these three don't give an integer value of A. And when B equals 6, we have that A is 32 times 6 over 4, which is 48. And the perimeter of triangle ABC is A plus B plus A plus B, which is 2 times 48 plus 6, which is 108. So are there any questions about this problem? I'm assuming there are no questions, so that was the final problem for today. And thank you for coming. And next week, please try to do the AIME practice test before time, because this time we only had a couple of submissions. Although it's fine because next week is also the AMC test week. So yeah, you can leave now if you want.